Okay, this next problem has a kind of a personal history with me. It's called the Norman window problem. And a Norman window is kind of like a church window. It's basically a rectangle that's surmounted by a semicircle. That's a pretty bad looking semicircle. Let's see if I can get a little bit better. A little bit better. Okay. And the reason this has a history is this was the last problem I remember doing when I was in my first calculus course in high school. And I remember having to go to the teacher over and over again for help and hints on it. And it just seemed so hard. And now, let's see, goodness, 45, almost 45 years later, it seems so simple after teaching it for 35 years or 40 years almost. So anyway, David Copperfield, the magician, once said that any person could do, any child, how did he say that? Any 8-year-old child could do his magic tricks with 20 years of experience. And so similarly, these things are all easy after you've done them enough times, thought about them enough. So here's what this one is. It's, as I say, it's a window in this shape. And let's say that I like to give a story that someone in a church donated, let's say, 12 feet of golden cord, which they donated to go around the perimeter of a window. And so the church was going to build a window, but they want to have as much light come in it as possible. So they're constrained by a 12-foot perimeter. But they want to have maximum area, okay? So let's see if we can do it. Notice it's fairly similar to the past problem, right? We're trying to maximize the area. So we'll go through the steps. So the first one is to, what is it you want to, you want to maximize in this case. You want to maximize the area. And so we need to come up with variables again. So we could let this be x, for example, and then the radius here would be half x. That would work. I prefer letting this be the radius r, and then this would be 2r. I prefer not having fractions if I can do without them. So this way it does away with that. So anyway, we'll let this be r, this is 2r. And let's let this be just y for whatever this height is right there, or h maybe for height, like so. Okay, so once we have that, then we can write the area, which is going to be a function of both of these things. It's going to be, first of all, the area of this bottom part of the rectangle, which is going to be 2r times h. And then it's going to be half of a circle. A circle is pi r squared, and you have half of it, so it's going to be pi r squared over 2. Okay? If you take pi r squared, which is the area of a circle, and take the derivative with respect to r, you get 2 pi r, which is the circumference. Is that a coincidence or what? It's not a coincidence. That's related to our idea of differentials. If you remember what we did with differentials, that's related. Here's another way, as long as I'm just taking a little break here. If you want to know what the area of a circle is, of radius r, just think of taking this circle and breaking it up into all these little pi wedges. Okay, so you break it up into all these pi wedges, and once you have them, these all are radius r. And if the radius r, we know that the circumference is 2 pi r. Okay, all the way around. And so if you take these and just take them and stack them up, they're going to look kind of like this. And you keep doing that all the way. I'll kind of exaggerate them here. Okay, until you're done. And now you look at what you get. You get yourself essentially a rectangle. And what's the area of that rectangle? Well, it's the length of the base, which is r, and then the height, and the height of it is going to be half of the circumference, because the circumference is being divided into those two sides. So since the length of one of the whole circumference is 2 pi r, this would be just pi r. So there's pi r times r, which is pi r squared. Isn't that cool? I came across that proof a while back, but that's really kind of a clever one. Anyway, here we go. So there's the area of this Norman window, and now the next constraint is, or the next step is, what is the constraint? And the constraint, again, is that the circumference, or I should say the perimeter of this whole thing has got to be 12. So, in other words, what do we have here? We have h plus 2 pi plus another h. And as I just said, the circumference of a circle is 2 pi r. So this is going to be just pi r for half of the circle there. Agreed? So let's go 2h plus 2r plus pi r. All that together has to add up to 12. Okay? So, the third step. Well, actually, part of the second step, I guess, is what we decided to call it, is that we're going to use this then to write a in terms of just one variable. So what can we do here? We can either solve it for r or solve it for h. Which would you rather solve it for? If we solve it for r, it's going to be a little bit harder because I have to first move this over and then factor an r out of those two, and you're going to get an expression for r, but it can be done. H will be a little bit easier because I just bring all this stuff over and I have h. So that one gives me the reason to solve it for h. A much better reason to solve it for h you get by looking up here. If I were to solve this for r and get some expression for r, then up here, wherever I see an r, I'm going to have to put this whole expression. Notice I'm going to have to square it right there, plus here. Much easier to solve it for h, and then I just put it in here. So either one of them would work, but one of them is a lot easier than the other one. So just kind of be wise as you do these things. So here we go. So I'm going to write this. I'm going to do it in one step. H is equal to 12 minus 2r minus pi r, all divided by 2. Agreed? 12 minus 2r minus pi r. Bring those over, divide by 2. So there's my h. So now, let's see, I can write this all in terms of just one variable. So that's the third step. And so how can you do that? You're going to get a, just as a function of r now, is equal to r times 2h. Well, notice that 2h is just going to be this thing right here, right? Twice h is going to be just that, so I might as well just put all that in there. 12 minus 2r minus pi r. Okay, that's 2h. And then what else do I have? I have 2rh plus pi r squared over 2. Okay, so now let's go ahead and simplify this if we can. We're going to get 12r minus 2r squared minus, can I do a couple things at once? Here, notice this is going to be a negative pi r squared. Then here I have a positive pi r squared over 2. So if I take this one and add it in with this one, I'm going to just get a negative pi r squared over 2. So there it is, all in terms of just one variable. So now let's go ahead and find out what the derivative is. The derivative is going to be 12 minus 4r minus, bring the 2 down, and it's going to be minus pi r. So there's the derivative. You set that equal to 0 because we want to know again where this thing is going to take on a maximum. And so you're going to get In fact, let's use the second derivative test. Second derivative test says this is going to be 12 minus 4. Oh, no, not 12. Take the derivative of that. It's going to be minus 4 minus pi, which is less than 0, which tells you that this is going to be a relative max right there. And since it's a relative max, and that's the only critical point, that means it's going down on both sides. So that's going to be what we want. Just by thinking about the problem physically, there's no way there'll be a relative min. The relative min would again be some extreme case, or I should say, no way this would be a minimum. The minimum is going to be some extreme case where you'd have basically no width at all and just a really long, narrow thing. So the max must occur in the interior of the interval at this critical point. But anyway, so here's this thing. So I set this. So let me just write relative max right there. So now I'll take this and set it equal to 0. So 12 minus 4r minus pi r, and again, never forget what you're doing. We just took the derivative. We had this function. We just took the derivative, and we set the derivative equal to 0. So I'm asking, where is that derivative equal to 0? That's where this thing is going to have a maximum. So the derivative, set it equal to 0. Solve it for r. We can bring these over. We're going to get 12 is equal to r times pi plus 4. And so finally, r is equal to 12 over 4 plus pi. So there's your radius. That's apparently the one that gives you the maximum value. Then if you want to know what the actual area is of the window, you'd have to take this value of r and have to stick it in here or here, I guess, just either of these formulas, and you'll find out what the area is. Okay, a bunch of algebra there. I won't even worry about it. Okay? Don't have time to or space to worry about it. Okay, but there's what you're after. There's the value, which is what, about 12 over 7, so about 1.5 feet is what r is. Okay, so pretty cool, kind of neat stuff, and each one of these is kind of a unique problem. Okay, that's good for this one. Next one is going to be a real applied problem having to do with strengths of beams. I'll tell you a dentist story about it coming up.